any other explanation. And there's further evidence that this is probably the case, because the Apollo asteroids seem to be refreshed. So again, the Apollo asteroids are the asteroids that are Earth-crossing asteroids, and they should have, or astronomers predict that they have a lifetime of about 1 million years, which seems like a long time, but compared to the length, or the time period of that the solar system has existed for billions of years, that's a very short amount of time. And so if we see them, we know that they had to have been replenished. So just like if you see an ice cream cone, right? You know that it must have recently been created, because an ice cream cone has a very short lifetime. Because if you leave it out of the freezer for too long, it melts and you don't see it. And so if you see ice cream cones, you know that they had to be recently created. And it's the same thing with the Apollo asteroids. The fact that we see them means that they must be being continually refreshed. And so if they were in this near, say, 3-to-1 orbital resonance with Jupiter, and then were knocked into the inner solar system periodically, that would explain why we see them. Where else can we see chaos in the solar system? Well, we see it in Hyperion. Hyperion is a potato-shaped moon of Saturn. It's a rather small and sort of uninteresting moon in that Saturn has a whole bunch of little moons around it. This is a view from the Cassini spacecraft as it flew by the moon Hyperion in its trip to the outer solar system here. And the interesting thing about Hyperion is that it rotates chaotically. So here's another image of Hyperion. I want to show you what that might look like. So what I mean by rotates chaotically is that, you think about the Earth or any other satellite, that it seems to always rotate around the same axis or in the same direction. Hyperion tumbles chaotically through as it moves around Saturn as it moves around in its orbit. And that motion is indeed chaotic. It never visits the same rotation axis twice, and it goes through all possible rotation axes, at least at some point during its lifetime. And interestingly, it happens to be in orbital resonance with Titan. Titan is the largest moon of Saturn. This is another little orbital resonance video here. And it's in a 4-to-3 orbital resonance with Titan. So for every, 4 times Titan goes around, Hyperion goes around exactly 3 times. And so it seems like near these orbital resonances, chaos can also be set up. Another place that we see chaotic behavior is in the satellites that surround the Earth. So there are literally thousands of satellites up surrounding and orbiting the Earth right now. From GPS satellites to television satellites to, super secret spy satellites are up there as well. And when we first started putting satellites into orbit, we noticed that there were some places where there was some satellite, you'd figure that all satellite trajectories are the same, right? What does it matter that it's going around this way versus this way, since the Earth is just one big spherical ball? But they discovered that certain trajectories or certain orbits were stable. The satellite seemed to stay in that orbit, where others, the satellite wouldn't behave, that it would just drift aimlessly. And they, and how do you, and if that's the case, if the satellite is just drifting aimlessly, that's expensive, because you can't go up, or it's nearly impossible to go up and service a satellite. And so whatever fuel you put on board for station keeping, that's all that you have. And so it would be useful or a good thing to put satellites in stable orbits. And how can we determine which those are and which ones are the unstable orbits? And this is so this made the cover of Science in 1990, so very prestigious work here. That this figure shows the stability of different orbits around the Earth. So if you think about this picture as a contour map, so like a hiking map that shows different elevations is all the same color. And so if you placed a satellite, say here, in this valley, it's going to stay in that valley. It's not going to be able to move up or down really out of the valley. But if you place the satellite here, now the motion is unpredictable, because sometimes the satellite will drift down this direction, sometimes it could drift down that direction, and either way it's going to wander from where you originally put it. So there are certain places that are certain orbits that are going to be better than others in which to place satellites. And this unstable motion is, for the most part, caused by the Earth's equatorial bulge. So just like when you put laundry in the washing machine in the spin cycle, and it flies to the outside of the washing machine, the same thing happens with the Earth as it spins around. With the equator, around the radius, that it gets a large bulge. It's actually not that large. The difference in radius between the poles and the equator is only about 20 miles. But it's significant enough that this small difference in mass can affect a satellite as it orbits the Earth. It feels slightly different gravity from that difference in mass as it moves around. And other uneven mass distributions can also have an effect. So if there's a particularly dense spot on the Earth, the satellite can feel that. And by mapping out these regions of stability, we can get an idea of what's going on inside of the Earth. Okay. So moving on. All right, so those are some examples of chaos in our solar system, or in our solar system. But recently we've discovered a whole bunch of other solar systems, and we've discovered that our solar system seems to be a lot different from the other solar systems that we've discovered. This is the first direct image that we have of another planet. This is the planet orbiting the star called Fomalhaut. I think that's how you pronounce it. And here you can see the planet. There it is right there. So here we have an actual photograph of another planet. And here it is in 2004, and you can see that it's moved a little bit 2 years later to 2006. We've discovered 497. Actually, discovered one more today, so it's 498. I was hoping that there would be a chance that 500 would be discovered just for this talk. And I was going to say, if 500 were discovered during the talk, then I'd take everyone out for a beer. But even though there aren't a lot of people here, I still probably shouldn't make that bet, because it's maybe more than I could afford to take out. But so 498 as of right now, or just shy of 500, which is really exciting. And of course, the reason that we're so interested, or so compelled to look for these other planets, is because we want to find one that is like the Earth. I mean, that's just natural human curiosity to be able to do that. And if we want to have a planet that's like the Earth, or could be habitable, it has to fall within the habitable zone. So what does that mean? So it means that, certain stars, so this star here is a red star is a little bit cooler, and so if you want life to exist, you can be closer to that star, so here's the habitable zone here. If it's a bright, hot star, then the habitable zone is further away, so that the temperature can be just right, that you could have liquid water, and the whole 9 yards. And and so that's also called the Goldilocks zone, because it's just right. Anyway, and we have actually found one planet in this Goldilocks zone. So here's an artist's rendition of it. We don't have a nice color photograph of it like that, of course, but it's actually not just one planet, but a system of planets orbiting a red dwarf star, so a star that's much cooler than our sun. And this star is only 20 light years from us. Keep in mind that the nearest star to us, Alpha Centauri, is about 4 light years away, and this one is 20 light years away. So if we wanted to, if there was life on this planet, we wanted to have a phone call or send a message to them. And I don't mean send them like a physical message or a letter, but if we could call them up, and by call them up I mean send them a radio waves, it would take 20 years for that message to get to the planet.